Thanks everyone for being here. So I was, invited to give this talk, and I actually should start with a bit of a disclaimer and perhaps even an apology, depending how, at sort of like cheated you feel by it, which is that, so when I was asked to give the title of the talk, I gave this a crash course on quantum information and quantum cryptography. And I was focusing on the quantum crypto part, so I actually was going heavily into like security proofs and things like that. But then, and now that you're here, I can actually sort of like confirm my expectations. So, how many of you come from sort of like an engineering background, like electrical engineering? Okay. Physics and maths. Okay, so I guess it seems like more like half and half. So I guess the engineering people, I guess, haven't seen, adding a course, an undergrad course on quantum mechanics, no? Yeah, okay. So I sort of felt the need whenever like I was going through the various steps of like going to the security proofs to actually go back and explain a bit of the theory behind quantum information, because and I'd say perhaps even especially if you had a course on quantum mechanics, like in a physics department, that might sort of bias your understanding of what is sort of like the modus operandi, in quantum information, which is quite different from what you usually are acquainted with if you did an undergrad quantum mechanics course. So I kept going back and adding more stuff on quantum information and more like really giving the foundations of quantum information theory, quantum information. So in the end, I got to a point where I guess the title of the talk would more aptly be, instead of a crash course, it doesn't. Okay, here it is. So instead of a crash course on quantum information and quantum cryptography, so actually, I think it's more apt to say probably a crash course in quantum information and some examples for quantum cryptography. Perhaps even the more apt title is if there's time. Okay. So what I aim to accomplish at the end of this talk is, even if you hadn't heard anything about quantum info at this point, that you would be sort of like in a scenario where you'd feel at least fairly well acquainted with the concepts and have sort of like at least some aspects of the tools that you need to actually go into. So I have to say I'm a theoretician, right? So to me, quantum info is, theoretical quantum info. So you won't hear much about, experiments or anything like that. So what I would like, especially since half of you come from more an engineering background, is to give you a solid theoretical foundation that then could aptly be applied to quantum cryptography. Okay. And actually, fortunately, historically, the birth of quantum information and quantum cryptography are the same. So they were sort of like spawned from the same event, and we'll actually go into some detail into the original paper that brought about the theory of quantum information and the theory of quantum cryptography. Okay, so as far as I'm aware, the first time that the words quantum information theory appeared, at least I don't know if they had been spoken before, but the first time that they had appeared were in these handwritten notes by Charlie Bennett. So for those of you that might know, Charlie Bennett is one of the Bs of the BB84, one of the founding fathers of quantum crypto and quantum information. And these notes date back to I think it's actually 1970. And it's a handwritten note about a conversation that he had with Stephen Wisner. And Stephen Wisner was essentially the father of quantum crypto and quantum information theory to some extent as well. And I'd like to draw your attention actually to the thing that's scribbled in the top right corner, where if you see very faintly in pencil, it's written false. So the story goes, so I have heard this a couple of times. The story goes that Steven Wiesner, he was working on, I don't know, I think he was working on completely other stuff, but he had a fairly good understanding of like the experiments of quantum mechanics. And at some point he wrote this report, which came to be the conjugate coding paper, which is this thing that you see here. In, I would say, the late 60s, about 67, 68, something like that. I'm not really sure on the dates. And he had tried to get it published, but he got rejected from a journal in IEEE, and he just put it in a drawer. Didn't mention to anyone until he met Charlie Bennett in a conference. And so the story goes that they were in the sea somewhere, and Charlie Bennett was there, and this guy swam to him and he said, I know how to make unforgeable quantum money, or something to that extent. And so, I mean, I guess they started talking, and these notes here are basically the notes that I guess Charlie Bennett wrote after their discussion, which pertains to the contents of this paper here, which was the paper of Steven Wiesner, where a lot of fundamental concepts were first introduced. Funnily enough, the very first line of the handwritten note, here it says a variation on the Einstein-Rosen-Podolsky Gedanken experiment. So if you actually go and read through the paper, I guess there's really no connection with the EPR paradox at all. So this is a bit of a curious fact that I actually don't know how this came to be, that the EPR thing is written on these notes. Okay, so just this to give you, this sort of like historical context, right? That quantum mechanics had already been around, so modern quantum mechanics since the 20s, since sort of Heisenberg and Schrödinger came up with their equivalent but distinct descriptions of matrix mechanics and the Schrödinger equation. And only some 40-something years later did like the first ideas that would come to be the founding ideas of quantum information came to be. But the math is the same. So why did it take so long to actually come to this conclusion? I would say basically that the difference is a difference in perspective. Okay, and so now I have this table here, and I would like to basically highlight the differences between quantum mechanics as you usually are taught in a physics department and quantum information theory as I'm going to explain it to you now, and as you would find in quantum information books like Nielsen and Schwang, and pick your favorite one. So some important concepts in quantum mechanics that if you go into a quantum mechanics course, you are bound to hear is particles, fields, spins, momentum, energy. So Hamiltonians, there's a lot of Hamiltonians there. So this generally refers to some sort of like physical stuff, right? That sort of believed to be real. So there's sort of like an implicit notion of physicalism, which makes sense because this is physics after all. So there are stuff like at the foundations that we sort of believe that are like the fundamental basic constituents of like reality, or what is it that we're sort of like trying to discover. On the other hand, quantum information, if you go into a quantum information course, the type of concepts and words that you'll hear is probabilities, entropies, correlations, information, okay? And so this has already a very different nature, right? To the things that, different character to the terms that we are seeing in quantum mechanics. So this information implicitly already compels us to think about agents and or experiments, and what we can know about the experiments. And so there's clearly already some sort of distinction here. So in terms of states and evolution, I mean, this is just like a particular example of the former, to be perfectly honest. So in a quantum mechanics course, what you have is basically you solve the Schrödinger equation for a lot of scenarios, right? So typically you have wave functions, describing physical systems that are represented in a continuous basis, either of position or momenta. And they evolve according to the Schrödinger equation, with some different types of potentials. In quantum information, what you have is more typically state vectors or even density matrix in the most general description, which describe registers of sort of abstract informational systems that evolve discretely according to unitary operations. Okay. I should mention, so if any of you have any doubts, you can interrupt me as I go along, okay? So like one, and essentially this is the core difference. The core difference is essentially the sort of like the philosophical stance between one or the other. Like quantum mechanics, which is a particular instantiation of quantum theory, is a physical theory. So it does abide to this implicit form of physicalism, right? It's a physical theory. On the other hand, the quantum information is not a theory, it's a framework to some extent. It's an informational theoretical framework. And you really care only about the things that are in the theory, which basically are useful to you with respect to the objective of why is it that you're using these things and what is the objective, what is the goal. So in quantum mechanics, the goal is sort of like to understand and predict physical phenomena for which quantum mechanics is required. So atomic structure, scattering processes, decays. And in quantum information, what you'd like is basically to have the possibility to manipulate and process information for tasks like computing, communication, and cryptography. Okay, so there's sort of like a more instrumentalist attitude, which basically the stuff in the theory is only useful insofar it allows you to do things that you want with it. And I guess this is why I guess in quantum information, like the spirit of it actually is, I seem to like whenever I talk to people that come from an experimental background or even engineering, they are much more quick to sort of like jump on like what's sort of like the general feel for quantum information than people that, like I did, that studied quantum field theory in my master's and had a hard time like doing this shift. So just to give you sort of like a visualization, what is it that I mean? So imagine that if you have a physical theory represented as this sort of like cylinder, like this hockey puck, and in particular, the physical theory that we're interested in is quantum mechanics. Sort of like we have sort of like a hierarchy of phenomena, okay, and of concepts and things. At the very bottom, we have the stuff that we believe to be real, right? This is the assumption of physicalism, that there are stuff that like particles, fields, energy, momentum. So these are entities that we sort of like believe to be out there in nature to some extent that we're trying to study. At the very superficial level, we have a completely strictly operational perspective, which basically tells you that really the only thing that matters is what you can measure essentially in a lab, classical inputs, classical outputs. And quantum information theory is closer to this top level than the bottom level, okay? I would not say that it's strictly at the superficial level because really when you're at an operational level, you're only talking about statistics. But so you still have an understanding of the inner workings of the theory from a mathematical perspective. But what you want is really to find ways how to leverage these things so that they are useful to you in some capacity. And the notion of usefulness basically depends on your desire. It could be useful for computation, useful for communication, useful for cryptography, useful for sensing, whatever you like, okay? Questions so far? So this is more or less like this, or like my philosophical introduction. But if you don't believe me, let me give you words of, more established people than I am. So in the Scott Aronson's Quantum Computing Since Democritus, he precisely tells, but if quantum mechanics is in physics in the usual sense, if it's not about matter or energy or waves or particles, then what is it about? from my perspective, it's about information and probabilities and observables and how they relate to each other. So from this perspective, Scott Aronson being a computer scientist, to him, quantum mechanics really is quantum information theory, right? Which is this other type of description where really what matters is like this emergent sort of like figures of merit, probabilities, entropies. So this is what really matters to us. So what is different between quantum mechanics and quantum information theory? The theory is the same. It's the same mathematics that we already had there in the 20s. The difference is a matter of perspective. So quantum mechanics, you have a physical theory grounded in a notion of physicalism. That is, it focuses on real physical systems and their properties. And in quantum information, it's an epistemic framework. So epistemic is a word that we often use when we want to sound smart. Basically, it comes from the Greek. It just means that which relates to knowledge and information, okay? So it's an epistemic framework concerned with studying the manipulation and processing of information emergent from the quantum mechanical phenomena, okay? So this is as simple as I can sort of like delineate what's the difference between quantum mechanics and quantum information theory. It's just a matter of perspective. So it will be useful to conceptualize quantum information as a theory of processes, okay? And when I mention processes, I actually mean boxes, black boxes with inputs and outputs, and they can be connected and you can sort of study their inputs and study their outputs. But we don't really care in great detail about the inner works of the boxes. We don't. I mean, that's, you know, I mean, if you're an experimentalist, you should, because you need to really understand what's going inside the box. And if you're trying to, you know, construct new detectors, new sources, obviously you need to know that the way to generate an entangled photon is with some type of crystal, and that is, you know, spontaneous parametric down conversion or whatever it is. But if you're a theoretician like myself, you don't really care much about those things. So you conceptualize an ideal box that gives you a quantum state, okay, to some extent. So we can have a good understanding how the boxes behave with respect to their inputs and their outputs, such that we can model them within the formalism of quantum mechanics consistently with the observed behavior of the boxes. So we have, you know, the machinery of quantum mechanics, and we use that to sort of model what's the behavior of these boxes, okay? So the inputs and the outputs. Typically, one tries to be as agnostic as possible about the context of the boxes, so we don't really care much about it, but sometimes it's fair to establish general assumptions, like assumptions about the dimension or the energy of the state that's being outputted by the box, okay? So going back to my original question, so why did it take so long going, you know, assuming that, you know, 40 something years, it's, you know, a fair amount of time in the, you know, time scale of science. So why did it take so long to go from, you know, quantum mechanics to sort of like change in perspective in quantum information theory? And really, it was basically because we hadn't this perspective yet. And what happened is basically, I guess this perspective, although seemingly naive, can be very useful psychologically in a very specific sense. So if you are in quantum mechanics, the type of stuff that you would look and frown upon with respect to the things that don't really make as much sense as you would hope it would, with respect to, say, coherence, superposition, right? Measurement incompatibility, entanglement, non-locality, okay? This is the most extreme example. So these things, which were frowned upon, looked as sort of like undesirable things in the theory, can be transformed into resources, things that we can use. So sometimes if most of you probably have heard the sentence, it's not a bug, it's a feature, right? So this is more or less in a very, very summarized sense. This is a change of perspective, like whatever it is that makes quantum mechanics conceptually more different than what we were dealing with in classical mechanics. It doesn't really have to be a burden. It can help you in some way. So instead of being a bug, it's a feature. which I guess from this image, essentially it's a well-dressed bug to some extent, which basically just, gives you the idea that the bug is the same. It's just really a matter of perspective. So now let's go into the actual matter of fact, quantum information theory. How can we conceptualize then this theory, like as a process theory with black boxes? Okay, the first one is preparations, okay? As we are more or less all familiar with preparations, I decided to pick specifically deterministic preparations, which are easier and you don't lose generality over it. In any sense, those are most likely the type of preparations that you do have when you're doing experiments in a lab. So preparations are boxes. So I put them here like this light shade of gray that have a classical input, so represented by that arrow going into that knob, which basically, so X is an element of some alphabet, some list of symbols that you give into this box. And basically the box, I don't care what it does, but I know that when I give a specific symbol, X, it outputs something, a quantum state, okay? The notation color-wise is basically that whichever is quantum is in green, okay? So like the output of the preparation box is in green because the output is green. Okay, so if any of you are in a lab, maybe this looks more familiar to you. Okay, so this is a preparation. You give some input, you plug in some computer, you tell it what to do, gives you some output. But let's define things rigorously. Okay, so a preparation is formally characterized by a Hilbert space, which is that boldface H there. And if you don't really know mathematically what a Hilbert space is, don't worry. So in quantum information, typically we are infinite dimensions. So the Hilbert space is essentially a complex Euclidean space. So it's a vector space, just like every other vector space that you dealt in your linear algebra class. But instead of having, just real numbers, like, Rn, it can have also complex numbers. So the vector can also have complex numbers as well. And so basically, like the typical structures that you have in a linear algebra, like in a linear space, you have vectors, that you have linear operators, and they all can basically have these complex components. Okay. So the Hilbert space is implicitly defined because it has basically to have it gives you the couch on where the state can live. And after you have the Hilbert space defined, you need to define a class of density operators, okay? So basically one for each of the x's that you can have if given as input to the preparation box. And density operators are essentially mathematical objects which are positive semi-definite, trace one Hermitian operators that act on the Hilbert space, which is implicitly defined by the box. So let me go through every which one. So hermiticity basically means that the complex conjugate is equal to its own. Positive semi-definite means that essentially the spectrum cannot be negative. Okay, so you have this interpretation of the density operators as giving you probability. So probabilities cannot be negative. And then you have the trace condition, which basically means that for a closed system, this has to be normalized to 1, which is basically just a normalization condition for probability. Okay, so if you have a box and you give me, like, you specify, okay, here's the inputs. The box is such that when you give it this input, this is the output. And then I go and compute for the specific output that you gave me, the outputs for every possible combination of the X respect these 3 conditions, then I'm completely assured that this is a preparation within sort of like my operational theory. Okay. Questions so far? So let me give an example. Okay. So we need first to define a space. Let's define the simplest non-trivial one, which is the qubit space. So this is a 2-dimensional space that you're probably acquainted with. I basically it's the span of any two orthogonal vectors that you'd like that span the base the space. You can represent them as vectors. So here 0 in column notation, it's the 1 0, and 1 is the 0 1. And then you have, after you have the Hilbert space defined, you define the states there. So actually I should do that right, because then you don't see. Okay. So for this particular box, this preparation, I instantiated a box that gives you 4 possible outputs, depending on 4 possible classical inputs. So you have 1, 2, 3, 4. For input 1, it gives you this 0, 0. If you don't really know what this means, don't worry. For 2, it's this 1, 1. For the 3, it's this plus, plus. And for 4, it's the minus, minus, where the plus and the minus are vectors in this Hilbert space, which are given basically by this expression, and you can compute them explicitly in column form if you just substitute the 0 and the 1 as you have here on this side. Okay. Okay, so this thing here, it's a density operator. It's actually a projection. You can compute explicitly these matrices. So these are the matrices that represent the states that are being outputted by my preparation procedure. Okay, I specify, this is what I specify. I have a preparation procedure that does this. I go through the definition. If the definition is correct for each of possible outputs given the inputs, then I know that this is correct. And this is the beauty of being a theoretician, because I sort of like by decretum, I say that it is like this and it is like this. So I don't have to worry about noise. I don't have to worry about like, is the thing plugged in or something. Like, it's basically, I define it to be as such, and it respects my conditions, then I know that it has to be a preparation in my theory. Whether then the preparation can be then reasonably implemented in the lab or not is something that then it's up to more experimentally inclined people to figure out. So this specific instance of this preparation is outputting what we call pure states, which basically means that the density operator is given by an outer product of a unique vector in the Hilbert space. Okay, so everything is given by like just this ket bra. It's what we sort of like we'd call it. So probably you've heard the bracket notation if you have had the course in quantum mechanics, which is the inner product. The ket bra is the outer product, and basically you can compute it explicitly with the column vectors, and you get these matrices here. Okay, so far so good. Questions? No. So what does the box do? It's not very not very interesting box. I just given an input, x equals 3. I know that it will deterministically output a state, which is here. I actually just wrote the vector, so in vector form, but you can just write it as a density matrix as well. And we're done. So I have this box. This is the behavior of the box. I give an instantiation how the box behaves for this specific input. This is a preparation in my theory. Okay. So now that preparations are taken care, let's go for transformations. Okay. Transformations essentially take a quantum input and give you a quantum output. And they can also have a classical input or not. If you want to basically, if they have a classical input, they're a control transformation. So you can basically select whether like the specific transformation for a choice of your classical input. The only difference is basically that whenever you're computing the output of the state for a controlled transformation, you should take care and have like this subscript C such that okay, this is this function for the specific C that I programmed it to behave as such. If you don't have a control, basically it's a global transformation, so it behaves the same regardless, what's of the protocol. It's a fixed transformation. So in the lab, it might look something like this. I don't know. I just search for, polarizing filters. I don't know if this is the type of thing that you deal with, but so this would be, I guess, the transformation that would correspond to a rotation of the Poincaré sphere for if you're basically describing polarization of a photon or something like that. Okay. So let's define properly things. Okay, I like to define things properly. So just like in the preparation, you have to have the Hilbert space defined. Okay, the Hilbert space, and this is a subtlety for a transformation, does not need to be the Hilbert space of the state for which it came from the same preparation. So if you're plugging in, I'm already getting ahead of myself, but if you plug in a preparation to transformation, the transformation itself does not need to live exactly in the same Hilbert space than the transformation. It could have different dimensions, but let us assume that it's exactly the same. So I'm assuming that the Hilbert space dimension of transformation in whichever setup I am is exactly as it needs to be to account for a transformation over the complete Hilbert space of the state that's being given as an input to the transformation. Okay. So in this scenario, a transformation then is described by a set of completely positive, so a control transformation for each of the possible classical inputs that you give is defined by a completely positive trace preserving map. This is a map from the Hilbert space to the Hilbert space. And this is fairly, abstract, but fortunately very good mathematicians found out a way that we actually can have a computable equivalent way of doing these things, which is that for any possible completely positive trace preserving map, there's a set of operators called Krauss operators that basically in the cross representation, you can decompose the effect that this CPTP map, as we call it, has on the state as a sum of these Krauss operators acting on the states that was given as input to the transformation. Okay, so this, have any of you seen this thing before, like CPTP maps, cross representations? No. Okay, so essentially, you have these matrices, and these matrices have to respect some properties, and these properties are basically precisely, if you give a quantum state which respected those properties that we saw before, positive semi-definite, trace one, and what was the other one, hermeticity, when the state that comes out of a transformation needs to be a density operator as well, okay? So that it is a transformation in the theory. Otherwise, you're transforming things to outside of your, conceived theory, which is not good. So in order for you to have like this sort of like soundness of your composition process, the cross representation or like the CPTP maps need to be such that, it has to be positive as well, so that you don't have the negative probabilities at the output of the transformation. It needs to trace preserve, so that the trace is actually the same as the trace of the input state before. So if this trace was normalized to 1, this means that the trace after the transformation is also 1. So very well, this can still, the elements of the density matrix can still be interpreted as probabilities, normalized probabilities. And in order for this to be the case, then we can show mathematically that the Krauss operators need to respect this property here, which is that their sum of the emission multiplied by itself needs to basically give you the identity on the Hilbert space. Okay, so this is basically an equivalent condition for like the previous completely positivity interest preserving of the CPTP map implies this on the Krauss operators. Okay. So let me give you an example. Okay, examples are always good. Okay. So the space is the same as the space of the preparations. It's a qubit. It's a two-dimensional system. And these are the transformations. It's a control transformation. So I basically have two CPTP maps, which are specified by an input. For the first input, the CPTP map, I define it to be such that it's the identity. Okay, so it's not very interesting, doesn't do anything, but sometimes it's important. The second one, it's what we call, so it's this matrix here, it's the Hadamard operation. Okay, maybe you've heard of this. Such that if the input that's given to the controller transformation is 1 when receiving a row X state, basically means that the output will be the row X state because it's just the identity. Okay, the identity doesn't do anything to the operator. If it's the input was 2, so I selected for the second input for my control transformation, then basically the output will be this, which is the original state that was given as input, transformed according to this Hadamard matrix and whatever it is that it does. So we are in a special case where these cross operators are actually unitaries, which means that there's only one of them. Okay, so the property of the sum having to be equal to identity just becomes that the operator itself times the emission needs to be equal to the identity. Okay. So an example, row X, given input to the transformation, I select C equals 2. I have this output, which is row X transformed according to the Hadamard operation. So far, so good. Okay. So finally, but surely not least, so these are the most like layered black boxes of our theory. We have measurements. So measurements are like this. So measurements actually have both a quantum input and a classical input, and a quantum output and a classical output. Okay. The quantum inputs and outputs are represented in green, as I told you. And so what happens is basically you get this classical input that selects a specific measurement that will be made on row X. But as I'm sure you know, these measurements are usually give you probabilistic outcomes. So you get a B, okay, which is some output. And then you have a post-measurement state, which is the state after the measurement has been applied. Now, sometimes you might want to recycle this post-measurement state. There are scenarios where this is actually needed and interesting, but most of the times probably you don't need to, so you can just assume that you throw it in a trash, okay? So sometimes we don't care about the post-measurement state. Sometimes we care about the post-measurement state. Okay. So this might look like something that you like. So this is a measurement. So as it is sort of like in the lab. So let's define measurements. So as per usual, like in the previous two cases, we have to have the Hilbert space implicitly defined for the system. And then you have a positive operated valued measure. So for each of the possible classical inputs that you can give to the box. So positive operated value measure is a set of POVM, so of elements, such that each element has to be positive semi-definite, Hermitian, and acts on the Hilbert space H. Okay. So hermeticity we have already seen, positive semi-definiteness as well, and then they have to sum to the identity. Okay. Now, as I told you, measurements are usually probabilistic. So the way to compute probabilities with the measurement is by this rule, which is called the Born rule. Okay, the Born rule basically tells you, if you have a row X state, okay, that was given as input to the measurement, and you selected the Y POVM that basically specifies the measurement, the probability that you read out of the classical input of that measurement P is equal to the trace of row X, the state that was given as input, times the POVM element of that POVM that corresponds to that output. Okay? I sort of feel that I lost you there. So I'll try to say again. So measurements have a classical input, okay? The classical input will basically select a POVM. So a measurement is a collection of POVMs, not just one POVM necessarily, a collection of POVMs. It's like the unit transformations. It's basically you can choose which POVM you are applying depending on the classical input of your measure, of your measurement. Sorry. Then, having the POVM selected, the probability that you read a specific output is given by the Born rule, where you compute the inner product, which is basically for operators given in this trace, given by this trace of the state, and the POVM element that corresponds to the output that you classically read out of your measurement device. If you didn't get that, I'll try again in the example, okay? Mm-hmm. Yes. So for a non-destructive measurement, the post-measurement state is computed by this thing, which is a fairly awful expression. So basically, each POVM element can be decomposed by a cross representation as well, like in this case for the CPTP maps. And you can compute explicitly what the output state of the post-measure of sort of like the post-measurement state after the measurement has been made by this expression here. So we have the rho x. You have to figure out what the cross representation is for the POVM element that corresponds to the classical output you saw. And then you compute this expression and you have the post-measurement state, okay? And so obviously the post-measurement state will be in general probabilistic because the output that you will see classically will also be probabilistic given by the Born rule. So there's also the case of destructive measurements where basically there's no post-measurement output, okay? This is usually the case, and actually is the case for this type of measurement that's like the box here for my DQ, because I think this is a photon quantum number. And these are measurements that essentially destroy the Hilbert space, if you'd like. Okay, so there's no system after the measurement has been done. The quantum system disappears when the measurement is made. So operationally, if you have a measurement which is non-destructive, but you trash the output, this is equivalent to a destructive measurement, okay? This is equivalent. And I'm just using this so that I don't have to carry out the trash icon throughout the rest of the presentation. But this is actually, so there's a formal proof that you can make to show that this is true, that if you have a measurement for which you have a post-selected state, but you discard it. So in a protocol, you put it in the trash, you don't use it. This is the same as if you had a measurement which was destructive, okay? So now let me give you an example of a measurement. So like in the previous cases, I'll give you a fairly simple one where the measurements are actually going to be what we call projective measurements, okay? So projective measurements mean that the POVM element, when multiplied by itself, is equal to itself. Okay, this is the definition of a projection. So the POVM elements here are basically, so there's two POVMs, okay, because so Y can be either 0 or 1. So I have two POVMs. So my measurement is defined by two POVMs. To each POVM, there's two elements, okay? The first element of the first POVM is given by this. The second element of the first POVM is given by this. The first element of the second POVM is given by this, and the second element of the second POVM is given by this, okay? So now I have this measurement, I have a state, I have this Y binary Y input for these POVM elements that I've defined. And the output is actually going to be binary as well, because there's two POVM elements, so there's an output associated to each POVM element. So since every POVM has two elements, the output is going to be 2 as well. So computing the probabilities, what you get is basically that the probability, so for a specific X which parameterizes the input state to the measurement, if Y equals 0 is chosen, which means that I'm using the first POVM, the probability that I get a read of 0 is given by the trace of that POVM element times the state, which is, if you recall, just this thing here. So I have this. The same for each of them, okay? So now here I actually computed the post-measure, I put explicitly the post-measurement state because fortunately, the post-measurement state for projective measurements is much easier to compute than for general POVMs. So the post-measurement state when a projective measurement is applied is just the state that corresponds to the classical value that you saw. So imagine that you do a measurement, okay? There's a state that comes in and you do a projective measurement and the output is 0, and such that 0 is the classical element that's associated to the projection onto the 0, the ket-bra 0, 0. The output will be the ket-bra 0, 0, okay? You can actually, if you plug in the definition that I just previously showed you, that ugly one. So if you put here, because what will happen is that the cross representation of the projections will be the projections themselves. So you can plug them directly here, and this will give you very nicely just the output state that's associated with the classical value that you saw. Okay? Okay. So let me see how much time I have. So any questions now? No. Okay. So everyone's getting everything perfect. Yeah. So yeah. When you say that you projection measurement, you can relate that to the classical value that you. Yeah. So in projective measurements, you could have projective measurements with the generic, which correspond to the same eigenvalue. What you'll have is that so what you have. So in this case, I think you're correct. In this case, they should be non-degenerate. If I can give you an example of a non-projective measurement on a two-level system. There's nothing to write on. I don't have anything. But so if you know, sort of like the elements that go into computing the noise in a completely depolarizing channel. So the matrices are POVM elements which are not projective. Okay, I can then show you afterwards. Okay. So but essentially, so I guess this should be enough to sort of like satisfy. So what will so a non-projective element, the POVM element will need to have at least two. So sorry, for a non-projective POVM, the POVM will need to have at least more than one POVM element. Okay, so this is the thing. So you'll have to have at least, so for one POVM, you'll have to have one POVM element and the other POVM element. So you need two of these, as opposed to the projective ones where I'll just have one. Okay, so which is the projective measurement itself. So yeah, I mean, it's difficult to explain in words. I can show you afterwards. But okay, so we have these three boxes. Okay, you have preparations, you have transformations, and you have measurements. I guess now the question is, how can we connect and compose these boxes with one another? Okay, the rule of thumb is the following. Quantum outputs can connect to quantum inputs. So this is sort of like where I guess the foresight of having used the green color comes in hand. Basically, so this the less than or equal notation is basically just to say that the one on the left can be composed to the one on the right. So for preparations can be composed to transformations, and preparations can be composed to measurements. Okay, because you have a preparation, the preparation gives you a quantum state, then that quantum state can go through a transformation, or the preparation gives you a quantum state, and that quantum state can go through a measurement. Okay, so transformations can be composed with transformations. So state comes out of transformation, can go into another transformation, and then transformation can be composed to a measurement. So state comes out of a transformation and goes into a measurement. Now measurements, I put them here in parentheses because then these are basically for non-destructive measurements. So if there's an output of the quantum state, so for a non-destructive measurement, measurements can actually be composed with measurements because there's a quantum state at the output of a non-destructive quantum measurement, and it can go to another quantum measurement, and it can go to a transformation itself. Okay, but this is contingent of the fact that the measurement should not be destructive. So my question now is, you have one preparation, one transformation, and one measurement. How can you basically draw a sketch that actually uses every which and of them? Basically, the only way is this. So you have a preparation. The preparation gives an output specified by X, goes into a transformation. Here, I just put a global transformation, so I did not put a control transformation. So there's a CPTP map that acts on the state that was given by the preparation, and then this transformed state goes into a measurement, which here I assumed was a destructive measurement, so there's no post-measurement state. You give a classical input to the measurement, and you get the classical output out of the measurement. So this is called a prepare, transform, and measure scenario, which is fairly self-explanatory why. And now you can use the Born rule to actually compute the probabilities of this experiment. Okay, this is an experiment essentially. Okay, this is an experiment idealized in my operational theory for these primitives, which are these boxes that I have. So the probability of you reading a specific B value, given a specific Y value for the measurement that you chose to operate on the state, and for a specific X that gave you a specific state out of the preparation, is given you by the Born rule, as same as before, but now the state is the transformed state. Okay, so we have the phi state transformed on the rho X state, and basically you have the POVM element that corresponds to the measurement that you're seeing for B. Okay, so now let me basically tell you something, which is that transformations, although they might be useful in some scenarios for respect to information processing and devising new protocols, they are actually fairly inconsequential with respect to the operational theory. And this is because transformation can be absorbed into a preparation. Okay, so essentially you can idealize sort of like you glue in the output of the preparation and the input of this transformation, and then you have a novel preparation, this P prime, which is sort of like inside of this light shaded region, which is a new preparation which specified on X gives you already the output transformed on. Okay. So just to give you an example, so imagine that you have a preparation which basically only has a binary input, and it either prepares the state 0 or 1. And then I have a control transformation that, depending on my input, applies either the identity or the Hadamard operation. Essentially, this will be equivalent to the first example of the preparation where I show you, where you have an X going from 1, 2, 3, 4, and basically the preparation is 0, 1 for the 1. So for X equals 1, the preparation will be the ket bra 0, 0. For X equals 2, the ket bra will be 1, 1. And then if you have 0 with C equals 1, it gives you the preparation that was for X equals 3. So let me just go back to show you. So if you recall, for preparations, we had this example, right? So for row 1, you have 0. For row 2, you have 1. For row 3, you have plus. And for row 4, you have minus. So this precisely matches the outputs of this composed preparation that I have now, where I have the more limited preparation that just outputs 0s and 1s, but then I have this transformation that applies the Hadamard or not. And essentially, if you don't know, the Hadamard, what it does is that if you apply it to 0, it basically turns it into a plus. If you apply it into 1, it turns it into a minus. So either you apply a transformation and you have 0, or you have a plus and a minus, or you don't apply the transformation or apply the identity, right? And you get the original two states that came out of the original preparation. Okay, so this is true for preparations. This can be formally shown. I'm just giving you an example. I'm not, showing any type of proof. And this can actually be shown as well for measurements. So measurements, the same rules apply. Basically, you can imagine that you plug in immediately the output of the transformation into the input of the measurement. And what you have is a different measurement that's being applied, which basically, instead of just being the POVM element that of the original element, it will be that composed with the CPTP map of the row X. Okay. So ignoring transformations, we really only have two ways to just basically two orderings of the ways that we can connect the boxes. You can either connect preparations into measurements, or for non-destructive measurements, you can connect measurements to measurements. Okay. So just with one preparation and one measurement, there's only one thing that we can do, which is this. Okay. This is called the prepare and measure scenario. So even the names are very easy to remember, right? Because they're self-explanatory. And now you just compute the Born rule, and you have the statistics that for a specific input for the preparation and a specific input for the measurement, and a specific output for the output of the measurement. But then my question is, so if you have two measurements, what can you do? Okay, in following these rules here of composition, essentially, you can sort of like conclude that you can put the measurements like this. If the preparation gives you, gives an output of an entangled state, so you send part of the state to some measurement, part of the state to another measurement. Okay, so this is called a bipartite Bell scenario. This is important for, non-locality. It is essentially the archetypal scenario for non-locality. It's important, these types of, if you haven't heard, Bell's inequalities and Bell's theorems are important for a branch of cryptography, which is called device-independent cryptography. Okay, so you can do this. Then you can actually try to compose things which are not quantum. So you can actually compose the quantum channels itself, and you can actually compose that such that the output, the classical output of the measurement, is given into the input of the other measurement. Okay, this is bipartite. This is still the same scenario, the bipartite Bell, but with restricted classical communication. Okay, but really the only other way that we can sort of like connect the one preparation into measurements is like this. Okay, if the middle the measurement in the middle is a non-destructive measurement, then it gives you a post-measurement state, and you can give that to another measurement. And these are basically sequential scenarios, which sequential measurement scenarios, as they are known, which are useful for the study of various types of inequalities, which, similar to Bell's inequalities, study other types of correlations that derive from this scenario. So in this case, Leggett-Garg inequalities and Cauchy-Specker contextuality, and temporal correlations as well. So, but now the question is, so what about three measurements? Okay, and for three measurements, you can have what's called a tripartite Bell, which is the same as like in the Bell scenario, but now you send instead of an EPR pair, meaning like a 2-qubit entangled pair, you send a tripartite state, and you have one going into Alice, the other going to Bob, and then to Charlie. Okay, so you have like the measurements in parallel. Then you can have a bipartite hidden on local scenario. So this is where you have one measurement on one side, and then you have two measurements on the other sequentially. Okay, so it's a mixture between the bipartite Bell and the sequential scenario that we saw. Okay, then you can still have the sequential scenario with three measurements. Okay, but now you can ask, okay, but why only like increase the number of measurements? Let's increase the number of preparations as well. And then it becomes like this, huge mess. For two preparations and up to 4 measurements, you already are in this network non-locality scenario. And basically, the simplest example is this bilocal scenario. You have entanglement assisted preparing measures. So essentially, there's a lot more. Basically, if you increase more preparations, there's a lot more. If you increase more measurements, there's a lot more. And reduced to a caricature, sort of like the operational perspective could be read to say that quantum information is basically finding interesting way to connect the boxes. of your theory. Okay, this is sort of like if I wanted to give it as sort of like as the shortest way, probably not the most accurate, but still captures a essential feature of it. Quantum information, taken from this sort of like operational perspective, is finding interesting ways to connect the boxes. Quantum cryptography then is finding interesting ways to securely connect the boxes. Okay, so for a notion of security that depends entirely on the setup. So, but let's go back to the prepare and measure scenario, which is actually, although simple, very important for quantum cryptography. So in this case, I'm assuming that you have two inputs, both are bits. They specify a state that I'm not actually explicitly what it is. Then there's a measurement for that has a classical input, which is a bit, and also gives you a classical output, which is a bit. But so you already defined some preparations and some measurements before in the example, so might just see if we plug these two together, what we get out of it, okay? So if you recall, the preparation that we had defined was basically this one, okay? And the measurements were this, okay? Which are essentially the same as the preparations. And now you can compute probabilities, okay? So it's they are not too difficult to compute, but just like taking a look at them all at once might be a bit frightening. But essentially, what this tells you is the following. So imagine, like, let's take one at a time. If S1 is equal to 0, so S1 is the second bit here, okay? S1, the way that I parameterize the states basically means that if it's equal to 0, so meaning this case here, in this case here, that the states will be either 0 or 1, which means that it will be states that are basis states in the computational basis. Now, if y is equal to 0, and y equal to 0 basically means that the projections are going to be projections onto the computational basis. What this means is basically that the probability that the output of this experiment being equal to the input, basically because the input encodes sort of like the value of the classical bit. So 0, we have 0 here, 1, we have 1 here, and here you have plus because it's encoded in the other basis, and here you have minus because it's encoded in the other basis. But the probability that you get is the value is when you measure. So the value of S0 equal to the output of your measurement is going to be 1 if you do the measurement on the same basis of which the states were prepared. Okay, this is fairly straightforward and saying in words. And so the probability that it will be different is going to be 0. Now, on the other hand, if you're going to, okay, let's see if I can manage to get there. If you're going to measure in the other diagonal, in the other basis, the diagonal basis, this basically means that if you compute the probabilities, that you'll have 1/2 probability that the bit B is going to be equal to S0, and 1/2 probability that bit B is going to be different than S0. And this lower half of the table is precisely the same, but now I'm just changing, okay? Instead of like in this first one, the states were prepared in the computational, and I'm measuring the computational to get the deterministic bit. Here, I'm measuring in the diagonal when they're preparing the diagonal to get them. So anyway, just to recap, you just compute inner products of matrices and you basically get the probabilities. It's not too difficult. The important thing to notice is here, basically, if you measure in the basis of which the states were prepared, you get a deterministic output, which corresponds to a classical bit, which is encoded into the first index of the state, so S0. If you measure in the basis, which is the sort of like not the basis where the state was prepared in, you get no information. So basically, in the sense that it's as likely that the bit is going to be S0 and as likely that it's not going to be S0. Okay, so this phenomena basically is based on a notion which is called mutually unbiased basis or conjugate basis. And so the computational and diagonal bases are an example of mutually unbiased bases, and essentially they are bases for which if you project one state onto a basis which was not the state, the basis where that state corresponds to an eigenvector, the probability that the state gets projected to either of the eigenvectors of the other basis is going to be uniform. Okay, and is actually going to be, 1 over the dimension. So in this case, since it's a qubit, you get 1/2. So it's sort of like the maximal ignorance projection that you can have. You get no information out of it. Okay, so I showed you the example of the conjugate paper in the beginning. So let's go back to the conjugate paper. So the conjugate coding paper, basically the idea that bears its name is this. This is the words of Wisner's. Conjugate code is any communication scheme in which the physical systems used as signals are placed in states corresponding to elements of several conjugate bases of the Hilbert space describing the individual system. Okay, so this is precisely the example that we saw here. Okay, so we are transmitting row S0, S1 to be states that correspond to basis states of these conjugate or mutually unbiased bases. They are more famously known nowadays. And this idea basically is essentially the core idea that's behind, the majority of the early cryptographic primitives. So this is behind the first quantum oblivious transfer protocol that was proposed. This is behind the BB84 quantum key distribution protocol, if you ever heard the name. And even more recent work, actually from a student from ITI Verde, I know some of you might know, Manuel Santos, that he actually has a quantum oblivious linear evaluation, which was just recently published with people from Lisbon, so Paulo Mateus and Riso Avelar. And essentially the core idea for which they make that, on which they stand on to make this protocol work, is precisely the idea of mutually unbiased bases in very high dimensions. So not in dimension 2, but very high dimensions. But even in the original conjugate coding, so Wisner gave this idea of conjugate coding, and he gave 2 examples where conjugate coding could be interesting. I'm going to show you the first example, which is this, example 1. A means for transmitting 2 messages, either, but not both of which may be received. Okay. So let's imagine the following. You have a string 1, which corresponds to a message that you want to give to someone, send to a receiver, and you have string 2. Then you do a quantum encoding for string 1, and you do a quantum encoding for string 2, such that the encoding of the bits on string 1 corresponds to either the 0 or the 1 state in the computational basis. So if you have a 0, you basically have a corresponding 0 state cat. If you have a 1, you have a corresponding 1 state cat. For string 2, for the 0 state, put the plus state, for the 0 bits, you put the plus states, and for the 1 bits, you put the minus states. Okay, and so what's the idea that Wisner had in order to exploit this, this conjugate coding idea? So imagine that you have some I number of rounds. At each round, you sample a uniformly distributed bit. So here I put 1 and 2. Okay, basically corresponds to no, so actually it should be 0 and 1, but it doesn't really matter. So you uniformly sample 1 and what did I put? Okay, yeah, sure. You sample 1 and 2 uniformly, and depending on the value, basically this will define out of which ith bit you're going to send of the string that corresponds to the value of the R that you sampled. Okay, let me say it in other words. Imagine that I'm doing the second round. Okay, I sample this, I get 1, so it means I'm going to send the second bit of the first string, which means that the encoding will be the zero state. Okay, so as a preparation, what this tells you is basically that if you have a preparation and you at each round give basically this value I, so this I here, this square brackets means, you know, the index of the string, right? And for the uniformly sampled bit, basically you'll give this to the preparation process, and the preparation process will give you precisely the encoding for that bit that corresponds to the RI you sampled. Basically, if it was 1, it will give you a state which is prepared in the computational basis, depending on the value of the ith bit. If it was a 2, it will give you a plus or a minus, depending on the value of the ith bit. Okay? Yeah.
Sure that you received one message.
Yes, no.
They must be easy.
Yeah, yes.
So it's not the same as doing like, I choose between 1 and 2, and if I get 1, I send like the qubit from message 1 and the qubit from message 2, and if I have 2, I do the opposite, I send 2 and 1. Because in that case, you know that if the messages are following, after the double the size of the message, you are sure that you send all messages. You have one message.
Yes.
So in terms of the security.
So in terms of the security, for this setup specifically, it will be the same, but in general, I don't think it is the same. Because here the setup, so this is only secure in a very strict, trusted model where the measurement has to be fixed. And if the measurement is fixed, it's true that this scenario is also secure in the same way. So essentially now you want to send this information to a receiver, and the receiver, what it has is basically just a bit. Okay, so it fixes the measurement to be the same for all possible ith rounds. So basically that Bob's measurement is not so good. Okay, so it cannot like basically do sort of like, you know, round by round adaptation. So it's a non-adaptive measurement, and it fixes the measurement globally for all possible rounds. So basically what Bob's decision is either I measure 0, which basically depending on the measurement, but here I'm assuming it's going to be a measurement over the computational basis, recovers the bits of string 1, or either I measure in the diagonal basis and I measure some bits of string 2. Then there's going to be a lot of noise, because then you're going to measure bits in the diagonal basis that, you know, were encoded in the computational and vice versa. But the idea is, if in the end, Bob can either recover a noisy string 1 or a noisy string 2, according to his choice, because it's the choice of the original of the fixed measurement that it shows at the beginning of the protocol, but not both. Okay, and he cannot recover both, and he has no information about the other message, precisely because of this conjugate coding idea, that if the site, like the bits that were corresponding to string 2, if he decided to measure string 1, are completely random to him, because they're going to be 1/2 probability of being the bit that actually was encoded, or the opposite. So he has no information. So this is the best case scenario. This is unconditional security. Okay. Furthermore, Alice won't know what message Bob desired to recover, because she has no information. Okay, so the sender has no information. So this is already a 1 out of 2 OT. Okay, so just the first example of this conjugate coding, you already have a 1 out of 2 OT, years and years before Rabin's first proposal of the OT in 91. Okay, so if you don't know, a 1 out of 2 OT is precisely this that I sort of like described. You have two parties, you have a sender, you have a receiver. The sender sends 2 messages, so 2 strings, to this oblivious transfer functionality, such that the receiver can only recover 1. And when he recovers like whichever one he decides to, so message 1 or 0, if he decides to recover message 0, he has no information, or he should have no information about message 1. And on the other hand, the sender should not know which message the receiver received or asked for. Okay, so this is precisely what we have here. So the sender, by sending this conjugate coding like this, has no information about the value of Y, because it's basically just, it's in Bob's personal laboratory. And if Bob has this very weak measurement, then he has no information about the other string. But the issue is that this is so this is what we call sort of like a trusted model, where we have a physical assumption which is made over the way that the boxes operate in some sense. And although this protocol is actually perfectly secure for malicious sender and malicious sender or Alice, so you cannot have a better notion of security for an OT than the one that you have, just like in this conjugate coding scheme that Wisner proposed. The security against the receiver is very, very weak. It's secure only against, like in formal terms, against a semi-honest receiver for a trusted model of non-adaptive single qubit measurements. Okay, so this is very bad, because generally you can do collective measurements. And so this is essentially the problem that then afterwards Bennett and collaborators solved in order to actually have the first formal proposal of a secure OT, which was introduced in 91 or 92, if I believe. But what I want to basically just impart on you is that although the details of like how can you make this more secure, and you can make this more secure either by imposing other more sort of like favorable assumptions on the trusted model, or you can actually have some computational assumptions that constrain, like having one-way functions or something like that. The crucial feature of every one of these protocols is this idea of conjugate coding, so that you have states that correspond to information that's prepared in one mutual unbiased basis. When they are measured in another mutual unbiased basis, you have no information about anything. Okay, and so this is basically the quantum magic that is given to BB84, the quantum magic that's given to the OT of Bennett and collaborators of 92, which is basically just a formalization of this idea that Wisner already had. And in anything that uses this type of states and this idea, basically this is where it boils down to. This is where the quantum stuff comes into play. It's this conjugate coding. So then I guess I'll go into the details of how you could actually prove security in more favorable models, like with better assumptions. But for this, I think I'm already way past my time. So for now, I just want to thank you for your attention.